Hello, everyone. In this video, we'll talk about normality and random events briefly. The idea here is really an idea from something called the central limit theorem. And that's a very important theorem in statistics, probability theory, um, and it's a very interesting theorem. And basically, what it says is that if you have something that is a particular type of experiment, and you repeat it over and over and over again, and it's independently done each and every time, that what you'll tend to have happen is the results of that experiment will start to look like a normal distribution, no matter what they look like initially. So you'll start to see things over time uh, build up to a standard normal distribution. That's what accounts for, that fact is what accounts for such prevalence of this type of distribution in statistics and in nature. So one example of such an experiment is flipping a coin. And what is discussed in the section in the book and is generalized a little bit there, um, along with a few other examples, is uh, what happens when you have a simulation run that just flips a coin over and over again. What we're looking at here is a computer output of a simulation of 1,000 tosses. That's the experiment, and they repeat that experiment 100,000 times, and they get a picture like this. So each experiment, they count the number of heads after 1,000 tosses. And what you're looking at is sort of the distribution, or histogram, if you will, of the results. And so what you'll see in general is this kind of phenomena. And this section discusses it. So now let's talk about a particular example, and we'll go through an exercise using that, the information that we have from that particular example of a dishonest coin. So a dishonest coin is, well, it's not necessarily an honest coin, and it has a certain probability of landing on, say, heads, which may not be 50%. So we'll say with probability P landing on heads. And then we're going to set up a variable or an experiment, if you will, which we'll call X. So what is X? X is going to equal the number of heads in n tosses of the coin. So what does this mean? So if we want to get one of the data points in our set, we call it X, and we would flip the coin n times, and we would record how many times that we got heads in the n times, and that would be our X. And so again, what you're looking at in this picture is n equaling 1,000. That's our n. But P in this case, this is a fair coin picture. P in this case is 50 or zero point 0.5 if you want to do the probability, 50% or zero point 0.5. So the result, which follows from the central limit theorem and some of the other statistical analysis, is that you get an approximately normal distribution with mean. So then the result is an approximate normal distribution with mean mu equal to n times p, and standard deviation equal to square root of n times p times 1 minus p. And so from this result, you can calculate all kinds of interesting phenomena. So there's actually, this is sort of, it may look like a silly example, but actually this example can model a lot of different situations where you have a binary choice, a choice of one or the other with a certain probability leaning in one direction. And then you have to repeat that choice over and over and over and over again. You can then use a standard normal distribution along with this mean and this formula for the standard deviation to calculate certain probabilities of the outcomes. So let's do a particular example with this, and then we will wrap it up. Okay, so let's suppose, we'll call this an exercise. We'll suppose that a given coin, dishonest coin, has a 10% chance of landing on heads. What is the 84th percentile? Well, we'll do all three. We'll do the 16th, 84th, and 97.5th percentiles of if you were to flip of x if n is, say, 1,000. So we'll do 1,000, no question mark here, sorry about that. If we do 1,000 flips of this coin, what is the 97th percentile of the number of times it will land on heads? So in a fair coin, you would certainly imagine that to be, uh, fairly large. We can calculate that separately, but it would be, I don't know, 700 times or something, certainly above 700 times, like 900 times or something of that sort, 950 times. I don't know. We can calculate that separately, but let's see what these numbers are for this case. Okay, so again, whenever you're doing a model with a standard normal distribution, you need to calculate your mean and your standard deviation. And so those are the two numbers that you'll need whenever you're going to talk about standard normal distributions. So the solution here will be mean is going to equal n times p. So I said n is 1,000, and I said p is 10%. That's the probability. So I'm going to move this up so we can read it. So we're going to multiply, but we always turn that into a decimal form. So it's going to be 0.1. So the average here is going to be 100. That sort of makes sense that there's a 10% chance of landing on heads. We flip the coin 1,000 times. We expect that, 1/10 of that 1,000 is when we're going to get heads. So that's 100. The standard deviation is going to be the square root of the number we just calculated, but we'll write it out, 1,000 times 0.1 times 1 minus 0.1. So that's 100, square root of 100 times 0.9, or the square root of 90, which is approximately 9.5. So now if we want to calculate these percentiles are chosen so that they are integral multiples of the standard deviation away from the mean. So in a standard normal distribution, we can calculate these. P 16 is equal to mu minus sigma, which is equal to 100 minus 9.5, which is equal to 91.5. Oops, 90.5. P84, on the other hand, we add sigma. That's 100 plus 9.5, or 109.5. And then finally, the 97.5th percentile is we're adding 2 times sigma, which is 100 plus 19, or 119. So what does this tell us? It tells us that there is a 97.5% chance that the number of heads will come in less than 119, less than or equal to 119 times. We flip it 1,000 times, and there's a 97.5% chance that we'll get less than or equal to 119 heads. So that actually, I think, is kind of surprising that it's that probable of getting such a low number of heads, even though you'll have a 10% chance each time. Maybe you would expect you would have some higher probability of getting a few more heads. So this kind of thing is applied frequently. It doesn't just apply to these binary experiments, but to a case where you could have many different outcomes from a single experiment. But if you have repeated trials, the central limit theorem says we're going to tend to a standard normal distribution.